Hello, welcome to the second video in chapter 1. We're talking about chemistry, the introduction to chemistry, and we just talked about what matter was. So we're going to talk more about matter, describe the physical states of matter and their properties, and then we're going to talk about how to classify matter. So let's go ahead and remember what the definition of matter is. Remember, matter is stuff. It's anything that has a mass and occupies space. Matter is disposed of discrete, tiny, fundamental particles called atoms. Okay? So the smallest particle of matter that exists that has properties of that matter is an atom. And these atoms can combine if you know about chemistry. We'll talk more about that. We're just going to keep the basics right now. So an atom, if you have, for example, let's say a copper coin, and the elemental symbol for copper is C, capital C, small u. We use symbols in chemistry a lot rather than writing out the whole word. It's very simple. But let's say you have a copper coin. Copper is an element. It's a type of matter that consists of only one type of atom. And the atoms composed in that coin of copper are copper atoms. All right, keep it simple. They're the small little particles of copper. Atoms, and they're the discrete particles, which means they can't be divided any further. The smallest particle of copper is a copper atom that you cannot subdivide any further, or else you'll lose the properties of that element, and you release a lot of energy because you'd be dividing an atom, splitting an atom. So atoms are the smallest particle that give matter its properties. Let's talk about the physical states of matter. There are 3 physical states of matter: solid, liquid, and gas. And when we refer to solid, liquid, and gas as the physical states of matter, which I know you've heard of, we usually use an S for solid, a small L for liquid, and a small G for gas. Alright? Does all matter occur in 3 phases? No. For example, sugar, or C6H12O6 will say, it's a solid at room temperature. If you heat it up, but it doesn't actually melt. It starts to decompose or break apart. So it doesn't actually become liquid. If you ever think you've seen liquid sugar, you've probably seen sugar that dissolved in a little bit of water. So you have a solution of sugar and water, which gives it its liquid properties. But really, it doesn't have all 3 phases. Now, a lot of compounds can exist in all 3 phases. One example of matter that exists in all 3 phases is water, which you probably know as H2O. 2 hydrogens and 1 oxygen. Now, when we write H2O, the H stands for hydrogen, the O stands for oxygen, and we'll cover this in chapter 3 when we get to elements and compounds. But there's 2 hydrogens and 1 oxygen chemically combined together. I always say that water kind of looks like Mickey Mouse. So you've got your oxygen atom, and it's chemically bonded to 2 hydrogen atoms. And that's the most discrete particle. It contains 3 different atoms, but it's called a molecule. And we're going to be looking at how that molecule of water is arranged in the solid, liquid, and gas phases. The solid phase of water we know is called ice. The liquid phase of water we usually just call water, but if you want to call it liquid water, that's fine. And the gaseous phase of water is called steam. Right? If you look at the particles in these 3, so here we have ice. Okay, if we take some microscopic goggles and we put them on, and we can see all the way down to the atomic level, what we'll see is a nice arrangement of particles that are closely packed together, and they're not really moving around. If we look at the liquid water particles, what you'll notice, and this isn't in 3-dimensional, in time, but you still have the packing of the particles. But instead of being non-mobile, they're moving around, slipping and sliding over each other. And what we notice in the gaseous phase of water is that the particles are relatively far apart. And if I had a movie, they'd be moving around very quickly. So in all 3 of these phases of matter, we have water, H2O. But the water is behaving differently in its motion and its compactness. And these give us the 3 different phases. So let's talk more about the properties of solids, liquids, and gases. And we'll start with solids. Remember how to write solid in shorthand, because shorthand's your friend in chemistry. It's a little s. Sometimes put it in parentheses. But solids, in solid matter, the particles are tightly packed together and they're not mobile. So just like the ice, those particles are touching one another, tightly packed. And the particles are not slipping and sliding around each other, but they're staying in place. The forces of attraction in the solid particles are very strong, and that allows them not to be mobile, but to stick closely together and stay together. So the forces of attraction between the particles exist is felt very highly in the solid phase, and there's not a lot of motion going on of the particles. Let's talk about the macroscopic properties. If you look at a solid, what do you see? Well, the first thing is the shape. Solids have a definite shape. They don't change their shape if you put them in different containers. If you take an ice cube and you put it in a beaker, it's still the shape of the ice cube in the beaker or outside of the beaker, right? It doesn't change its shape just because it's in a different container. If you put an ice cube in a dryer, it's still an ice cube. It's still got the cubic shape. All right, so the shape is definite. The volume, how much space the particles take up, because they're tightly packed and they don't move around, it's going to stay the same. It's a definite volume. An ice cube doesn't expand or compress, so it's non-compressible, virtually, because the particles are already tightly packed. You can't push them any closer together. So in general, they keep their shape and they keep their volume, regardless of the container. Now, there are two different types of solids if you look at the microscopic level in which the atoms or particles can pack. The first is a crystalline solid. Crystalline solids have the particles arranged in a very irregular repeating manner. Down here, we have an example of a crystalline solid. Do you see the organized pattern of the particles? Right? Those are crystals. Like if you ever look at a crystal or through like something that's very crystalline, it's because at the atomic level, those atoms, those particles are arranged in a very regular manner. It's very beautiful because when the light shines on a crystal surface on these atoms, because they're so regular in arrangement, the light either reflects beautifully from them so they look shiny, and sometimes you can see through things, crystals, because they refract the light at the same angle. It's not diffracted in several different directions. So those are crystalline solids, regular repeating patterns. The opposite of that is your amorphous solid. Now, you typically can't see through amorphous solids, or they're not shiny or something like that. Have you ever seen like carbon powder, right? Probably have. It's more amorphous. But if you ever seen like a shiny carbon, oh, very crystalline, right? Like maybe a ring, like a diamond. So it all has to do with the packing. Amorphous solids have no regular internal geometry. Okay, let's look at liquids. Liquids are always pourable, which means the particles are adhering to one another in some manner. If you pour a glass of water, you notice that the water doesn't float all over space when you empty it. The water adheres to itself, the water particles. So the particles are definitely in close contact. They have strong adhering properties. But what allows you to pour the water is the fact that the particles can move. They're mobile. It just doesn't dump out. It's pourable. Those particles are slipping and sliding against the surface of one another while they're in close contact. Now, what does this say about the shape of the liquids? Well, because they have strong adhering forces, not very strong like the solids, but strong, the shape, and because they're mobile, because the particles are mobile, the shape of the liquids is indefinite. They slip and slide around one another rather than not moving. So if you put them inside of a container, they are the shape of the container because they're slipping and sliding, and they collide and move back and forth as they hit the edges of the container or bump into one another. So they take on the shape of the container. Their shape is indefinite. What about the volume, the amount of space it takes up? Well, because liquid particles are still in close contact, they can't be pushed much tighter, all right? So the volume is definite. They're always in close contact. They always take up the same amount of space, regardless of their shape. And in general, liquids are virtually non-compressible. They don't compress or they don't pack tighter because they're already packed tightly. Okay, and that leaves us last with gases. All right, gases, the particles are relatively far apart compared to how small the particles are. The distance between each other is very large. And the particles are much more mobile than they even are in their liquid state. They have a higher energy mobility. So the particles are far apart. There's lots of space between them. They're not compact like they are in the solids of liquids. They're mobile like the liquids, though. Could you pour a gas? Yeah, you can probably pour gas, right? Because the particles are mobile from one container to another. It's kind of hard, but if it's a dense gas, you could do it. All right, let's talk about the forces of attraction then. Because the particles are relatively far apart, this tells us that the forces of attraction felt between the particles is very weak. In fact, in the kinetic molecular theory, what we learn is the particles behave independent of one another. And we'll learn that later on in the semester. So what does this say about the shape of a gas? Well, because the particles are moving around at a very quick pace and they have a lot of space between them, the shape or the arrangement of those particles in space and time can change. Therefore, the shape of a gas can change. For example, let's say that you have asthma and you have albuterol in a little inhaler. There's gas in that inhaler, and when you push it out, the inhaler has one shape, that gas is in there. When you breathe it in, where does that gas go? It goes into your lungs, and it fills up your lungs. Kind of like every time you breathe, you fill up your lungs with gas, right? So the gas can take on the shape of the container. If you have a tank of methane gas, or let's say, well, we'll just say methane gas. If you have a little tank and you crank that tank open in a closed room, the gas particles will seep out and then they will take up the entire space of the room, its new container. So they take on the shape and the volume of the container. So they have indefinite shape and indefinite volume. Gases are compressible. Because there's so much space between the particles, you can push the particles closer together. Hence compressed gas, right? Gas tanks, tanks that contain gas, they have compressed gas in them. That's why they're very dangerous, because there's a lot of pressure in there. And then if you open or let's say break the container, the gas comes out as the particles expand, right? All right, so these are the three physical states of matter: solid, liquid, and gas. Okay, let's move on to classifying matter. We know that matter can have three different phases. All right, but let's talk about if you have some type of matter, like a powder or some liquid, and you're looking at it, chemists need to know how to classify that matter for further investigation into its composition and its properties, things that chemists do. So let's talk about the different classes of matter. If you take any matter, you can put it into two different categories. You can either say that that matter consists of a pure substance or a mixture. It's either one substance or a mixture of different substances, all right? So let's look at a pure substance first. And I'm sorry I don't understand when I print this out what happened. The printer did not like what was on my computer screen. But, oh well, we will work through it. We will press on. All right. A pure substance is a substance that has a definite fixed composition, meaning there's only one type of particle present, one discrete particle present. So if you're looking at a sample, remember those discrete units we were talking about, the individual particles? If every individual discrete particle is the same in the compound or the composition of the matter you're looking at, you have a pure substance. There are two types of pure substances: elements and compounds. Elements, the discrete particles that are all the same, there's only one type of atom present in those particles. Okay, only one type of atom present in those particles. If you have a compound, the smallest particle consists of two or more atoms that are chemically combined, meaning stuck together. So here's an example of what I mean. Let's say you have this sample here, and it's a pure substance, because if you take all of those, there's 6 little particles there. Those 6 discrete particles are all 6 different atoms. You can pull them all apart. They're not chemically connected, and they're all the same. Because all the particles are the same, you have a pure substance. Now, why is it an element? Because if they all consist of just one atom type, you have an element. Now let's look at a compound. A compound has the smallest discrete particle, 2 or more elements chemically combined. An example of a compound is water, H2O. Water is a compound that contains 2 hydrogens and 1 oxygen chemically combined into one formula there. Here's 1 molecule of water. It contains an oxygen and 2 hydrogens. So if I took a water sample and I pulled apart all of the discrete particles, and look, there's atoms stuck together in them, all the particles are the same. 2 hydrogens and 1 oxygen in each of those particles. Therefore, it's a pure substance. Okay? Now, what type is it? If we look at that particle, it contains 2 different types of elements. 2 hydrogens and 1 oxygen. Because of that, it's a compound. 2 or more elements chemically combined. Alright? Let's look at some different examples visually. Here is sodium metal. Sodium is Na. Nah. Alright, so there's sodium there for you. Okay, sodium metal, shiny, kind of soft. If we were to look into the composition of sodium, if we were to get out our little molecular goggles and look really closely, we would see that all of the atoms in the element sodium are exactly the same. There's a whole bunch of little sodium atoms. So because they're all the same, we say it's a pure substance. Now, let's look at the smallest particle. The smallest particle is a sodium atom in there. It only consists of 1 atom type, sodium. Therefore, it is an element. Okay, let's look at chlorine. You've heard of chlorine gas, right? That's why you probably can't see it inside of the speaker. The chlorine gas is inside the speaker. But you can see through gases, because what are gases? Little particles, lots of space between them, so you can see through gases. Alright, chlorine gas has the formula Cl2. It consists of 2 Cl stands for chlorine. So 2 chlorine atoms chemically combined. Okay? So if we look in this flask, what we're going to see is we're going to have 1, 2, 3. Here's an example of 4 discrete or different particles. Now each particle has 2 chlorine atoms chemically combined. So my question to you, it's already written, but is this an element or a compound? A lot of my students will say it's a compound, but look at a compound. 2 or more different atoms chemically combined. I should say different. Here, let's write different. 2 or more different atoms chemically combined. Elements have only 1 atom type in each particle. Because this one particle contains a chlorine bonded to a chlorine, it's the same atom type. So technically this is an element. It's elemental chlorine. It's called a diatomic atom. Or element, sorry. That's a hard one. That's why I put it in the notes. I like to put the hard ones in the notes. They're in the book too. Now, what if I combine sodium and chlorine? Sodium and chlorine can be combined with electricity. They can make sodium chloride, aka table salt, right? Or salt. So sodium chloride is NaCl, alright? And the most discrete unit found in sodium chloride, we won't get into ionic versus covalent right now, but is these particles here. There's 2 different atoms that are chemically combined by something called an ionic bond. We have a sodium, the dark there, and then we have the light, we have the chlorine. So one discrete unit has 2 different atom types in it. So what is it? Is it an element or a compound? It's a compound. Now notice, element chemical symbols only have 1 type of element in them. Chemical symbols for compounds have 2 different types of elements in them. And we'll talk about elements in chapter 3. Alright? Okay, so these are pure substances. Pure substances, elements, or compounds. 1 type of discrete unit throughout the sample. Alright, so we said we had 2 different classifications of matter. Pure substances, all of the discrete particles are the same. And now we have mixtures. This is where if you take all the individual particles inside of that the composed substance, there's different discrete particles present. Okay? A mixture is a material that contains two or more substances. Notice it doesn't say they're chemically combined. They're just physically combined. They're mixed together. Okay? One of the things about mixtures is you can vary the composition of the mixture. And the other thing is that you can separate the components of the mixture by physical means. Physical means are not the same as chemical. You don't need to do a reaction. You can just use the properties of the substances to separate them. All right? For example, if you have salt and water and they are mixed together, the salt is still salt, right? If you drank that water, wouldn't it taste salty? Yeah, it didn't change its composition. It's just mixed in with the water. It makes a mixture. How can you separate salt and water mixtures? What you can do is you can use their properties. Water boils at 100 degrees Celsius. Salt is stable at that temperature. So what you can do is you can boil the water off, distill the water off, and you have the salt as a solid left behind, and you collect the water in another vessel. Another example is shown over here, and it's not in color because I don't have a color printer, but boo-hoo. This is an example from your text, so you probably read your textbook. There's sulfur powder, which is a bright yellow color, and that's that powder down there, and it's mixed with these iron shillings. All right, so we've got sulfur and iron. Sulfur, wrong, I need the pen. So we have sulfur and iron is Fe. And they are mixed together. Notice I didn't put SFE. That would imply that they were chemically combined on the molecular scale and they were one discrete unit. But because I put the word in here, it implies that there's a mixture of these two elements together. And that's exactly what it is. We can put in a lot of sulfur and a little bit of iron. We can vary the composition. Or we can put in a little bit of sulfur and a lot of iron shillings. Now, how can we separate iron and sulfur? Well, in this picture, they're taking a bar magnet, and what are they pulling out? They're pulling the iron out of the sulfur using magnetic properties. A physical property of iron is that it's magnetic, and sulfur is not. So these are just examples of mixtures and how they can be separated. All right, let's talk about the two types of mixtures. So we can either have heterogeneous mixtures, mixtures containing two or more distinct phases. Now, what are phases? We had to go over those a second ago, right? Phases are solid, liquid, and gas. Those are the phases we're talking about. Now, it says two or more distinct phases, where you can see those phases and they're different, okay? Maybe not really see, but you can know that they're different phasings. So we have heterogeneous. Heterogeneous mixtures are not the same throughout. Homogeneous mixtures are the same throughout. Okay, so let's look at examples here. Heterogeneous mixtures contain two or more distinct phases. The mixtures are not the same throughout. The first two examples I'm going to give are harder, which is why I'm going to give them. First example is ice water. Now, ice we know is H2O. Water is H2O. So most people might say, hey, that's a pure substance because everything's water. And they think it's like kind of obvious. But ice water is not a pure substance because there are phase boundaries between the ice and the water. And those particles cannot go in from one phase to the other. So because of that, we have solid and liquid phases present. We have two or more distinct phases. We have a heterogeneous mixture. Okay? Now, boiling water, same thing here. Boiling water consists of water in the liquid and the gas phases. Because we have distinct phases there, it's not the same throughout. Even though it's H2O, those particles are different. They're different arranged, they have different properties. So boiling water is another example because it's got two phases present of a heterogeneous mixture. In fact, anytime you have more than one phase distinction present, you're always heterogeneous. Okay. Another example is blood. People always like, what is blood? Well, you probably have to take bio or anatomy or physiology classes to know what all is in blood. There's plasma, you've got the water, you've got the liquids, right? You've got platelets that are solid, you've got your hemoglobin, which contains iron, solid. And what is that carrying? It's carrying gases, right, in your blood. So you've also got things like carbon dioxide and water being exchanged in your body. and being carried through your body. So you have gases, liquids, and solids. Blood has more than one phase present that's distinct. So it is a heterogeneous mixture. It's not the same throughout. All right. The next one is sand and water. I think by now that's kind of obvious. If you put sand and water, they don't mix. The sand goes to the bottom, water's there, and you could probably just separate it by filtering it, right? Yeah. What about oil and vinegar? This one's interesting because what is the phase of oil, like vegetable oil or cooking oil, olive oil? Any of those oils are liquids, right? What is the phase of vinegar? Or acetic acid, we'll say. Also liquid, right? So we have two liquids. Now, are those are phases, but are they distinct, two or more distinct phases? They are, because if you have ever made salad dressing in your fridge, okay, salad dressing, it sits in your fridge, and you know that when you put oil and water together, or oil and vinegar, actually I should say, both are the same, they don't mix. The oil and the vinegar separate out. And even though they're both liquid phases, there's a phase boundary where there's no mixing in between. It's not the same throughout, therefore it's heterogeneous. If you sipped on that, you'd get oil, 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 and then you'd get vinegar, vinegar, vinegar. The first sip's not the same as the last. It's not the same throughout. Therefore, it's heterogeneous. Two or more distinct liquid phases. Okay, so that one's interesting because there's two different liquid phases and they're not mixing. Let's talk about homogeneous mixtures. Homogeneous, the mixtures of different substances or different discrete particles, that's what a mixture is, have a uniform appearance. It's the same throughout. Everything is in the same phase. Okay, another word for a homogeneous mixture is a solution. You can use those terms for one another. You can either say homogeneous mixture or a solution. It means the same exact thing. All right, what are examples of homogeneous solution or homogeneous mixtures or solutions? Mixtures that are the same throughout, they're uniform in appearance, all in one phase. The first example I'm going to give you is air. Okay, what does air contain? It contains, of course, it's got nitrogen in it, it's got oxygen, we have some carbon dioxide, we have argon, it's got those traces, right? So, air contains several different, you could say this and this and this. It contains several different discrete particles, so it's a mixture. But if you breathe air on one side of the room, and then you go and breathe air on the other side of the room, do you have to worry about the oxygen contents of that air being off and your brain kind of shutting down because you don't have enough oxygen? No, because air is uniform. There's, 21% or something oxygen in air. So you don't have to worry about the composition of air. It's the same throughout all of the different gases. Therefore, it's a homogeneous mixture. It's an example of a gaseous solution. Another example of a solution or a homogeneous mixture is coffee. Or as the Northerners say, coffee, right? You got to go get me some coffee in the morning. Well, how do you make coffee? You get the grounds, right? And you put the hot water through, right? And you extract out from the coffee bean grounds, you extract out all of the flavor to make your coffee solution. If you look at coffee, it looks the same throughout, I hope, if you make it right. No chunks. But what's in there, you've got the water, and inside of that is dissolved the tannins and the flavonoids and the caffeine and the color, different colors, all from the coffee bean extract. So, all of that's combined. But if you brew a pot of coffee and you pour glasses, that first cup will taste like the last cup because it's a uniform mixture of all of those different extracts, right? You can have strong coffee and weak coffee as well. I mentioned that here. The fact that you can vary the composition, and I've had strong and weak coffee, and I like it right in between, I should say. But you can vary the composition tells you that it's a mixture, okay? But the fact that it's the same throughout, all in one phase, that's a homogeneous mixture or a solution. I think I gave an example of salt water before. That's a mixture, but it's a solution or a homogeneous mixture. Salt dissolves in water. Sand, we gave the example of sand and water. Sand and water don't mix, but salt and water do mix and they dissolve. Everything comes in the liquid-like phase, so you make a solution of salt and water at different concentrations. All right, so that brings us to the end of chapter 1. I would challenge you to go in your book, go find the extra problem worksheets, and you can look at the answers in the back of the book. You can look at answers in the worksheets. But I challenge you to practice as many problems as you can until you feel that you can do the material without having to look at your notes that you're taking or to use other resources to find answers. If you can find the answers with your brain, then you know the material, all right? Usually, students, for every 1 hour they spend in class, and if you're online, then you're going to spend, I think it's 4 hours a lecture, you should spend 3 hours for each hour outside of class studying. So that's why they call it like a full-time student. If you take 15-hour load, you're in class 15 hours a week, but then you're studying like 40 hours a week. It's crazy. It's hard, and it pays off. But just go ahead with chapter 1 and dedicate a time to study each week and practice problems. I suggest getting the content down first earlier in the week, practicing a few problems, putting it up, and then in midweek practicing more problems, and then doing the homework or the assignments that you're given for credit along with that, and then toward the end of the week kind of wrap it up. All right? And if you have any help, always ask people, like tutors, me, your classmates, but just start off the semester well. Chapter 1's a great place to start, and we'll look forward to learning some chemistry together, okay?